Hi everyone, welcome to this first ECON 333 tutorial. This tutorial is going to be done remotely, but starting next week, we'll be back in person with the TAs. In this tutorial, we are going to cover a bunch of different exercises. The first exercise is just a notation exercise, just to help us decipher what those big sums are. In the rest of the course, I will show you such formulas, so it is better to get used to using them and to seeing them right from the start. Then I will talk about some random variables. We are going to compute some expectations, some variance. We are going to look at some conditional expectations, some conditional probabilities, and that'll be it for this tutorial. So let's start with the first exercise, where you are asked to expand the following summations. So I call each of these summations S for sum, and I represent them with this uppercase letter sigma that you can find here. And note that these sigmas have some index at the bottom and at the top. This means that the index I is going to be the index that's going to be moving as we go along the sum. If a term doesn't have any index I, then it will not change from the first term to the second term. The upperscript index represents how far the sum is going to go. So for instance, let's start with the first one. The sum from I is equal to 1 to n of the number a means that when I is equal to 1, we have a term. Then we do plus the term when I is equal to 2, plus the term when I is equal to 3, all the way until when the term is equal to n. Typically, the best way to understand how summations work is to actually break it up, write 3, 4, maybe 5 terms, and understand where the pattern is. Here, we are summing up a constant every time. So, the index I is going to change, but there is no term inside the sum that is going to change. The number a is not indexed by an I. So in this case, the sum can be written as a plus a plus a, and so on. The first a corresponds to I is equal to 1. The second a corresponds to I is equal to 2. The third a corresponds to I is equal to 3, and so on until the last a that corresponds to the case where I is equal to n, the end of the sum. Now you will see that there are n terms a. So you can add all of them up and you will get the results, which is a times n. In fact, since this is a summation and the number a is inside every time, you can take the number a outside of the sum, like I do here, and replace what's inside the sum by the number 1. This is just a factorization. Remember that the sum is just a convenient way to write down a long formula. That's just it. So you put the a at the front of the sum, then you get a sum of ones when I is equal to 1, I is equal to 2, I is equal to 3, all the way until I is equal to n. So you will have 1 plus 1 plus 1 plus 1 n times. That gives you the number n multiplied by the number a at the front of the summation. Now, let's turn to a summation where there is an actual moving term. The simplest we can think of is the sum of the i's. First, we start with I is equal to 1. So I will be equal to 1. Then we put a plus, and then we replace I by 2, and that's going to give us a 2. Plus, the third term corresponds to I is equal to 3, and so on and so forth, all the way until we get to the last index, which is the number n. So, the formula can be broken up into 1 plus 2 plus 3 plus 4, plus 5, and so on until you get to plus n. Now, it turns out there's a formula to compute these things for an arbitrary n. If I give you 100, you can use a formula and that will give you the result of 1 plus 3 plus 4 plus 5, 1 plus 2 plus 3 plus 4, and so on, all the way to plus 100. If it's 200, 2000, or 20,000, same thing. You don't need to know it. This is just for your culture. This is what we call an arithmetic series. There is an easy way to compute it, and in fact, let's get to it. To see it, let's look at 2 times s. So let's multiply this thing by 2. But instead of just multiplying each term by 2, what I'm going to do is I'm going to do 1 plus 2 plus 3 plus 4 plus 5 all the way to plus n. And then I'm going to add again plus 1 plus 2 plus 3 plus 4 plus 5 and so on. I just repeat every number a second time. Now, note that the term before n will be n minus 1. If n is equal to 100, then n minus 1 is equal to 99. And now look at this. Here, you see I have an n plus 1. Now, I'm going to do 2 plus the term right before n, which is n minus 1. So n minus 1 plus 2 is also equal to n plus 1. Then I'm going to match the number 3 with the term before n minus 1. This term is going to be n minus 2. So 3 and n minus 2 will be equal to n plus 1 again. And so by matching the last terms of the first sum with the first terms of the second sum, I'm going to get the number n plus 1 many times. So I'm going to get the first n plus 1 coming from here, the middle term. Then I have 2 here plus n minus 1. That will also give you n plus 1. Then I have 3 plus n minus 2. That gives you n plus 1. Then I have 4 plus n minus 3, and so on and so forth. At the end, I end up with the last term here, n, plus the very first term here, 1, and again, another n plus 1. Now, let's count how many times we got the number n plus 1. We got it once here, a second time when I matched the 2, a third time when I matched the 3, a fourth time when I matched the 4, and by going this way all the way to the end, we're going to have it an nth time when we match the last n with the very first one. So the number n plus 1 will appear n times. So 2 times s, so 2 times this sum, will be equal to n times n plus 1 by matching all these numbers. Finally, since I only want to get the number s, I just divide the right-hand side by number 2, and I get n times n plus 1 over 2. Pretty smart, right? Look at an example. Imagine we have the sum of i's from I is equal to 1 to 4. That will be equal to 1 plus 2 plus 3 plus 4. If you do the computation by hand, that gives you 10. If you use the formula, you will have n here is equal to 4. This is the last term. 4 times 4 plus 1, which is 4 times 5. That's equal to 20. You divide this by 2, and you get the number 10 again. Note that this is a particular type of series, and it has to start with the number 1. And it has to increase by 1 every time. Of course, if you do 1 plus 3 plus 5 and you add all the even numbers or all the odd numbers, then there's going to be a similar formula, but you will have to play around and again match these numbers. Now, let's get into something slightly more tricky. That's actually a math concept, but I just thought I would put it out there just to show you how interesting some things can be. We take the sum from I is equal to 1 all the way to infinity of 1 over I. So let's break up this sum. It's going to be 1 over 1 first, then 1 over 2, then 1 over 3, then 1 over 4, all the way until infinity. So this sum will actually never end. And you can leave 3 dots here to say, well, it's going to keep going like this forever. The first number is equal to 1, the second number is equal to 0.5, the third number is equal to 0.3 or 0.333, the fourth number is equal to 0.25. So every time you add a new number, this new number is smaller than the previous one. And except for the first number, all the other numbers are lower than 1. 0.5 plus 0.333, which is smaller, plus 0.25, which is smaller, plus here 1 over 5 would be 0.2, which is even smaller, 1 over 6, 1 over 7, and so on. A typical question in math is, does this sum go to infinity? Because we are adding infinitely many terms, but at the same time, each term is smaller and smaller. Or does this sum converge? If we add more terms, does it converge to a single number and will never go beyond that number? This is an actual tricky question and requires complicated proofs sometimes to figure out whether something converges to a single number or, as we say, diverges, in the sense it goes to infinity. There are proofs that show that this sum actually goes to infinity. We are adding terms which are smaller and smaller, and they are all closer and closer to 0. But if you add sufficiently many numbers, you're going to get beyond the number 2 eventually. You're going to have to add a lot of them. But here you have 1 plus half makes 1 half, plus 0.33333, plus 0.25, so we actually go beyond 2 already. But then as you add smaller and smaller decimals, you might think we will never go beyond 3. Well, it turns out, if you add sufficiently many terms, maybe like 1,000, I don't know, this sum will go beyond 3, will go beyond 4, and so on. And so, this sum, although it looks like it will never go beyond 3, 4, maybe 5, will eventually go beyond these numbers if we add sufficiently many terms. This has implications in mathematics. When you think about compounding interest over time and other, especially financial mathematics and actuarial sciences, you do have a couple of terms that look like this, where I could be some sort of interest rate. Knowing whether this number converges or diverges will help you compute maybe your earnings over 10, 20, or maybe an infinite amount of periods. But let's go away from actuarial sciences, financial mathematics, and so on, and let's get back to statistics. The sum in D is the sum of random variables xi, and all of them are multiplied by 1 over n. So if you expand this sum, you get 1 over n, open the brackets, and then you get x1 plus x2 plus x3 and so on. Note that here, the index I, is not about what the number is, it's about which observation we are looking at. For instance, if I have a sample of 20 people, and I look at their weight, then I will add the weight of Mr. 1 with the weight of Miss 2 with the weight of Mr. 3 and so on until I get to my 20th person. Note that all of this sum is divided by n, so I can expand this sum into x1 plus x2 all the way to xn divided by n. This is the formula of the average of xi. This is the empirical average, the sample average, and we typically denote it x bar. You can see an upper bar here on the x, and this is the average x, the average weight, for instance, in my sample. We will go over this kind of summations very soon once we talk about estimation and inference. Once we talk about working with samples, we are going to deal with this kind of summation terms. So make sure you're comfortable with them. The last one I want to talk about for this tutorial is going to be used later on in the semester once we talk about linear regression. I don't want to explain to you what this means right now, but you will very soon understand what it means. Here I have a variable y, and I do yi minus xi times a number beta. Beta is just a fixed number, like a above, or alpha, whatever number it would be. And then I take the square every time. So if I expand the sum, and I start with I is equal to 1, then I have y1 minus x1 beta, and I take the square. Then once I am done writing the first term, I put a plus, and then I get to the second term. I replace I by the new index, which is 2, and I get y2 minus x2 beta squared, plus y3 minus x3 beta squared, and so on, all the way until yn minus xn beta squared. This computation represents a way to predict the variable y as a proportion of the variable x. It is called linear regression because here we have a proportionality relationship. We have a linear relationship between y and x. For instance, later on, we will see that y could be, for instance, the wage or the earnings of someone, and x could be the number of years of schooling this person had, their education. We want to predict the wage of someone based on this person's education, or this person's age, or this person's gender, and so on and so forth. So we'll try to predict the wage of someone using how much education they received. Beta will represent the best way to predict yi using the variable xi. And I'll leave the rest for later. Now, let's go back to probabilities. Consider a 6-faced die throw. So we have one die of 6 faces and we throw it once. We note x, the number we obtain when we throw that die once. And in this exercise, I ask you to report a couple of probabilities. It might be elementary, but it is a good way to just getting used to notation and making sure that we can write all the statements correctly. First, what is the probability of obtaining a 7? Well, if my die has 6 faces numbered 1, 2, 3, 4, 5, 6, then the probability of obtaining a 7 is 0. 7 is simply not a number we can obtain. So the probability of getting it is 0. That might sound trivial. That's just a warm-up. What is the probability of obtaining a number strictly bigger than 4? Well, here we have to count the number of successes and divide them by the number of possible outcomes. So, we have 6 possible cases here. The probability that x is bigger than 4 will correspond to getting the number 5 and the number 6. So there are 2 successes. There are 2 cases where we will say, yes, this is bigger than 4, divided by all the possible outcomes I can get, and there are 6 of them. So 1 plus 1 over 6 will be equal to 1/3. There is a 33.33333% chance that I will get a number strictly bigger than 4. Be careful, if I just said bigger or equal to 4, then we would have to include the number 4 as also a success. And then there will be 3 successes out of 6 possible cases. Now, what is the probability of obtaining a multiple of 3? Again, we have to count all the cases that correspond to a success, that correspond to a multiple of 3. This will correspond to the number 3. 3 is a multiple of itself, and the number 6. So we have 2 successes out of 6 different outcomes. This, again, will give us a probability of 1 over 3. I wrote here this in words. There is a mathematical way to write down something that is bigger, that is a multiple of 3. There's probably a fancy mathematical notation for it. I just don't really know it, and this is not very important for this course. Now, what is the probability of not obtaining a 1, a 5, or a 6? In this case, we are looking at the cases where x is not 1, not 5, not 6. Well, 2 is a success, 3 is a success, and 4 is also a success. But 5 and 6 are not, and 1 is not either. So 3 numbers will represent a success out of, again, 6 possible outcomes. The probability will then be 1 over 2. Note that we can use the rules on probabilities, the rules on complements, to compute this probability by taking it the other way around. Instead of looking at what x should not be, we can do 1 minus what x can be. So the probability of x not being this is equal to 1 minus the probability of x not being that. Here, in fact, there is a mistake. There should be a different here. And again, that would be a chance of 1 over 2. So 1 minus 1 over 2 will give you another 1 over 2. Okay. Now let's start some more serious business. Consider a random variable x, which follows a Bernoulli distribution with parameter p. Remember, a random variable follows a Bernoulli distribution when it's either equal to 1 with probability p or 0 with probability 1 minus p. So any binary variable equal to 1 or 0 is a Bernoulli random variable. And let's apply the couple of formulas we saw in the first lecture. What is the expectation of x? The expectation of x will be each outcome multiplied by the probability that they are happening. For x, there is a probability p that x is equal to 1, and a probability 1 minus p that x is equal to 0. It is very easy to see that the second term is actually equal to 0, and so the expectation will be equal to p. It is very, Bernoulli random variables are very easy to use. The expectation is always equal to the probability of obtaining a 1. Note that if you look at a sample of men and women, and you decide to transform this qualitative variable into a 1 or 0, into a Bernoulli random variable, let's say women get a 1, men get a 0, then the expectation of this sample data will be equal to p, the proportion of the people in the sample which are women, the proportion of ones. If women get a 1, then that will be the proportion of women. And vice versa, if you decide to attribute a 1 to a man. In the second question, we have to compute the expectation of x to the power of k for any integer k. So, the only thing that is going to change is what multiplies the probability every time. Here you can see x alone, and that becomes 1 here and 0 here. So if there is an exponent on the x, then each number that x can take will also take that exponent. So the expectation of x to the power of k will be p times 1 to the power of k plus 1 minus p times 0 to the power of k. Again, the second term is equal to 0, and the first term is equal to p times 1 to the power of k, which is equal to p. After all, a Bernoulli random variable either is equal to 0 or 1. 0 and 1 are the only numbers that you can raise them to any power, they stay the same. 1 to the power of 2 is equal to 1, 1 to the power of 1000 is equal to 1. 0 to the power of 1000 is also equal to 0. Now, we can actually use this property to compute the variance of x. I'm going to use the second formula because I already know the second term of the formula. Here there's a typo, that should be an expectation, and I will correct that. The variance of x is equal to the expectation of x squared minus the expectation of x squared. Note that I put a pause between x and squared in the second term. So, I already know the expectation of x. I found it here in question A. That's p. And I take the square, that will be p squared. Now, I need to compute expectation of x to the power of 2. But look at question B. Question B says that no matter what k is, as long as k is an integer, if k is equal to 2, the expectation of x to the power of 2 will also be equal to p. So I end up with p minus p squared, and this variance is equal to p times 1 minus p. Let's use the first formula. The first formula says I'm going to take the sum of the probability of taking each value times the value minus the expectation squared. So I get not p times 1 like before, but this time this 1 is going to be replaced by 1 minus the expectation, which is p, and then I square that difference. Then for the second term, it's going to be 1 minus p times not 0 alone, but now 0 minus p, and then because p is the expectation, and then I take the square of it. That might look a bit complicated, but you can rearrange terms. There is a p here, there is a here we're going to have a p squared, so I can take 1p out as well, and I am left with 1p here. Then inside the bracket I can just expand everything. This here will be equal to 1 minus 2p plus p squared. Here I'm going to have p minus p squared. And finally I can cancel out p squared here, and I am left with 1 minus 2p plus p. Minus 2p plus p is equal to minus p, and I get 1 minus p. Same result as before. So make sure you know how to manipulate both formulas, because they can help you double check your results in an exam. I strongly advise you to double check your results, because chances are that the variance of a random variable will not be the last thing you need to compute, and I might need you to use that variance for the following questions. So if you get that one wrong, you will get everything else wrong. So make sure you know how to double check your results early in the exercise. Chances are they will be useful, if not needed, to get the second part of the results correct. In fact, if you want to, you can also learn this variance by heart, p times 1 minus p. If you don't know it, hopefully you know how to compute it using either formula. Let's move on to another random variable, but we do not know its distribution. We only know that it has an expectation of 2 and a variance of 5. And we consider a transformation of this random variable. First we do minus 6, and then we multiply it by 0.5. This is what we call a linear transformation, because x is just multiplied by a constant. And then you add some kind of an intercept. Note that this is very common. For instance, in France and in Canada, temperature is measured in degrees Celsius. In the US, temperature is measured in degrees Fahrenheit. The conversion from one to the other is, I believe, 32.8 plus, or 32 plus 1.8 degrees Celsius. So, if you are in a place where it's actually 0 degrees Celsius, pretty much right now, where I am, it represents 32 degrees Fahrenheit. It's just a conversion. If you think about converting weight from kilograms to pounds, you have to take your weight in kilograms and multiply it by 2.2, and that will give you your weight in pounds. So this is pretty common. Now, given that we know the expectation and the variance of x, we want to know what the expectation and the variance of y will be. We are going to need to use the different properties we know about expectations and variance. So first, let's say the expectation of y. This is the expectation of the transformation. I just copy paste. Now, by linearity, I can take this 0.5 out because everything will be multiplied by 0.5. So I might as well factorize and put 0.5 in front. And I am left with 0.5 times expectation of x minus 6. Now, the expectation here applies to both x and 6. But since 6 is a constant, the expectation of it will be 6 itself, because it's always equal to 6. It is not a random variable. So, I can in fact just apply the expectation only on the x, and this is why I have the square brackets around the x only. Finally, I can just expand. 0.5 times expectation of x minus, from here, 0.5 times 0.5 times 6. I know that the expectation of x is equal to 2, so I replace the expectation of x by 2. 0.5 times 6 is equal to 3. I end up with 0.5 times 2 minus 3 minus 2. So if x has an expectation of 2, y will have an expectation of minus 2 because of this transformation here. Now, what is the variance of y? Again, the variance of y is the variance of 0.5 times x minus 6. Now be careful. If I want to take the 0.5 out, because we are looking at a variance and there is a square in the formula, I need to square this 0.5 up if I want to take it out of the brackets. So this is how I end up with 0.5 squared times the variance of x minus 6. Then, note that the variance of x minus 6 is the same as the variance of x, because 6 is not a random variable. It doesn't vary. a number that doesn't vary will have a variance of 0. So the variance of x minus 6 is the same as the variance of x itself. This would correspond, for instance, to a shift in the grade distribution. Imagine that the grade distribution has an average of 50%, and I decide to increase everybody's grade by 10%. So some people got 40, they go to 50, some people got 80, they go to 90, and so on. Now, the expectation will be 60 because I increased everybody's grade by 10%. But the variance around the mean, this 60%, will be the same as before. You can check this computation yourself if you want to. So, I know that the variance of x is equal to 5. 0.5 squared is equal to 0.25 times 5, that will be equal to 1.25. Make sure you know how to use these different properties. There is a very high chance that this will show up on the exams. Note that here, I do not know anything about the distribution of y. I do not know what the values that y can take are. I do not know what are the different probabilities. I just know that there is a relationship between x and y, and because the transformation is linear, I am able to deduce the expectation and variance of y based on the expectation and variance of x. Note that it would be difficult for me if here I had an x to the power of 2, 3, or log, or an exponential, because I know the expectation of x, but I do not know the expectation of log of x. And then it would be impossible for me to solve these questions. Let's get to the biggest chunk of this tutorial. We are going to look at the relationship between two random variables, x and y. Here, x can take the value 1 or 2, and y can take the value 0 or 1. Remember, the contingency table shows the joint probabilities. So, we start with these 4 numbers, and these ones are actually the answers. We start with, here this point 15 says, there is a 15% chance that x is equal to 1 and y is equal to 0 at the same time. Here, there is a 15% chance that both y and x are equal to 1 at the same time. Here, there is a 7% chance that x is equal to 2 and y is equal to 0. And finally, there is a 63% chance that x is equal to 2 and y is equal to 1. First thing we need to find, and first thing we should look for, is the marginal distribution of x and of y. Remember, the marginal distribution is the distribution of x alone. I do not want to know the probability of x being equal to 1 and y being equal to something. I just want to know the probability of x being equal to 1. And looking at this table, x is equal to 1 in 2 different instances. When y is equal to 0 and when y is equal to 1. So, if I want to find the marginal distribution of x, I can write down here p of x under the y's, and I can add all the probabilities where x is equal to 1 shows up. 15 plus 15 gives you 30, so there's a 30% chance that x is equal to 1. Same for x is equal to 2. X can be equal to 2 and y is equal to 1, and y is equal to 0, and x can be equal to 2 and y is equal to 1. When you add these probabilities together, you obtain the overall probability of x being equal to 2, and that's 70%. Note that since x can either be 1 or 2, when you add these two probabilities together, you get the number 1. So this table is great because it allows you to double check your computations in many different ways. The marginal distribution of y can be obtained the same way. For y is equal to 0, I'm going to add all the probabilities that contain y is equal to 0. 15% plus 7% gives you 22%. 15% here plus 63% gives you 70%, 78% here. Again, if you add these two probabilities together, you get a probability of 1. 1 is the probability of getting either a 0 or a 1. Since y can only be equal to 0 or 1, then you just add these two probabilities and it's equal to 1. There is a 100% chance that you are going to get a 0 or a 1. Same for x. There is a 100% chance that you are going to get a 1 or a 2. And this is what I show here. I add all the joint probabilities where x is equal to 1 shows up. And that gives me 0.3. I can do the same for x is equal to 2, which is what I did here. But I can also use another formula, again, to double check my computations. Since x can either be 1 or 2, if it's not 1, then it's equal to 2. And so, the probability that x is equal to 2 will be 1 minus the probability that x is equal to 1. 1 minus 0.3, again, gives you 0.7. And I did the same for the marginal distribution of y. This is kind of the first thing that you should do when you find a contingency table. You fill it up. No matter what probabilities you're given, which cell you're given, this one, maybe not this one, maybe not this one, and so on, fill it up entirely. There's always enough information for you to fill it up. And then from there, we can start answering more questions. Question B asks to compute conditional probabilities. Now things are going to get a bit tricky. What is the probability that x equals 2 given that y is equal to 0 or equal to 1? Here we need to look at a formula. We want to know the probability that x is equal to 2 when or given that we are already in the case where y is equal to 0. So note that we have this bar here to say given, and the formula for it will be the joint probability. This is the probability of x and y being equal to these values at the same time, divided by the proportion of y's which are equal to 0. Note that this y is equal to 0 here shows up down there. The same way this y is equal to 1, which appears inside the given, will show up at the bottom. It is my way to always remember the formula and not mix it up and put here x is equal to 2, for instance. We get 7% divided by 22%, and we get the number 32%. What this means is that among the observations where y is equal to 0, so we focus on the group of y is equal to 0, we don't look at everything anymore. We only look at the case where y is equal to 0. 32% of these observations have an x equal to 2. The same way I could say, what is the probability of finding a smoker given that I am looking at women? Now I focus on women. I don't look at men anymore. And I look at among the women, how many of them are smokers? That could be 50%. The overall probability of being a woman and being a smoker will, however, be smaller, as you can find here. The joint probability is smaller because when I look at joint probability, I am looking at the overall sample. When I look at a conditional probability, I am restraining myself to that subgroup. And this is how you hear, for instance, 20% of women smoke. It means, given that we look at women, 20% of them smoke. And I do the same for the probability that x is equal to 2, given that y is equal to 1. The top term is always the joint probability, and the bottom will be the marginal probability that corresponds to what's inside the given. From the table we have 0.63, that's this number, y is equal to 1 and x is equal to 2, divided by the probability that x is equal to 2, 0.7. You can imagine that this ratio is going to be pretty big. Because if you look at it, the number of cases where y is equal to 1 and x is equal to 2 is pretty high, compared to the case where x is equal to 2 and y is equal to 0. So, that will give you a solid 81%. 81% of the cases where y is equal to 1, we will also find that x is equal to 2. Question C asks to do the same thing, but this time we are looking at the probability that y equals 1 given x is equal to 1. So the first term will not be an x anymore, it will be a y, and the second term will be an x. But I can use the same formula, the same procedure. The joint probability at the top and the marginal probability at the bottom, and what's inside this marginal probability is going to match what's inside the given part, and so on and so on. Note that since here we have 15 and 15, the probability that y is equal to 0 when x is equal to 1 is 50%, 1 over 2. Because among the ones who, among the cases where x is equal to 1, half of them have a y is equal to 0, and half of them have y is equal to 1. We need these conditional probabilities if we want to compute conditional expectations and conditional variances. First of all, what is the expectation of x given that y is equal to 1? So we are restricting ourselves to the case where y is equal to 1. And this is why I have the given here. I can use the formula of the expectation. X can either be equal to 1 or 2. And every time we are going to multiply it by the corresponding probability. Here, because we have a conditional expectation, we need to include a conditional probability. So, this is going to be the probability that x is equal to 1, they match, given that y is equal to 1, that's our condition, plus the probability that x is equal to 2, here they match as well, given that y is equal to 1. Now note that we have computed this already. Careful, it is not this. Here we have y first, x second. Here we have x first, y second. We have to go higher. we have to go, wait. Oops, no, in fact, we don't have this probability. We have this one, x is equal to 2 given y is equal to 1. Here, we have 0.81 here. We do not have this probability yet. So make sure you are able to notice what we already know and what we do not know yet. So to compute this expectation, we need an intermediary step. We need to find this probability first. I can use the same formula as before. And I find, using the formula from before, that this probability is roughly equal to 19%. I can finally compute the conditional expectation, 0.19 times 1 plus 0.81 times 2. This is rather close to the number 2. Remember, x is between 1 and 2. Well, it's either 1 or 2. The expectation is pretty close to 2 because when y is equal to 1, and this is the condition we're looking at here, there is a very high chance that x is equal to 2. 81% chance. So that is going to draw the expectation towards the value 2. What is the expectation of y? Here, there is no condition anymore. I just want to know the expectation of y. At this stage, we have all the information that we need. Y can either be 0 or 1. So I'm going to do probability of being equal to 0 times 0 plus probability of being equal to 1 times 1. We found above that these probabilities were respectively 0.22 and 0.78. So the expectation of y will be 0.22 times 0 plus 0.78 times 1, and that gives you 0.78. Note that, well, y is either 0 or 1, so it's a Bernoulli random variable. And we know from the previous exercise that a Bernoulli random variable has an expectation equal to the probability of being equal to 1. This probability is equal to 0.78, and this is what we found here. Another way to double check your results. A third way would be to use the law of iterated expectations. I would have to take the expectation of the two conditional expectations. I would have the expectation of y conditional on x being equal to 1 on one hand. On the other hand, the expectation of y given that x is equal to 2, and then I would take the average of both, the expectation of both, to get the same number. Here, I do not do it because we haven't computed the expectation of y given x. We have done actually just the opposite, x given y. So if I wanted to use this formula, I would have to do extra work. Feel free to do so and let me know if you find the same result. If you don't, let me know as well, and I can help you compute the correct result. What is the variance of y? Well, again, there are no conditions here. So I can simply use the second formula. I quite like the second formula. Expectation of y squared minus the expectation of y squared. So with some probability, 22%, y will be equal to 0. And since here there is a square on the y, I multiply 0 by itself, so 0 squared, plus the probability that y is equal to 0 times 1 squared, and that will give you the expectation of y squared. Finally, we computed the expectation of y in the previous question. We found 0.78, and we just have to square it up. Finish the computations and you get 0.78. 17, 16. Two other ways to check your results here. The other way is to use the first formula. We have everything to get it done, and feel free to do it. It's always good to have extra practice. Or, again, you can use the fact that y is a Bernoulli random variable. So, since it takes a value of 0 or 1, the variance will be equal to p times 1 minus p. That's the computations we found in exercise 3. And if you do 0.78 times 1 minus 0.78, that will give you this result. Another way to double check your results. The bottom line of this tutorial is there are a bunch of tiny formulas here and there, and they all look very, very similar, but they all serve a very different purpose. So it is crucial that you know what each of them are, how to use them, and when to use them. The second bottom line of this tutorial is that you can double check almost all of your results, almost all the time. And I will design exams so that when you have probabilities, you should be able to double check your results, or you should be able to use two different ways to find the same result. No problem with that. Okay? So make sure you know this tutorial well. I will correct the couple of typos that I found and re-upload the solutions once it's done. Have a good rest of your week, and well, maybe not see you in the next one, but see you in person. Bye.